So we know this ligand can bind to this protein receptor, forming this protein-ligand complex. Then eventually the ligand's going to pop off, reforming the free ligand and free protein receptor. Then it's going to bind back on, reforming the complex, and then it's going to fall off. And eventually we're going to reach an equilibrium. However, you may wonder, how can we characterize the affinity that this ligand has for its protein receptor? Does this ligand bind tightly, or does it barely bind at all? How would we objectively characterize and measure that affinity that the ligand has for the protein receptor? Well, something important to realize is every ligand and protein receptor interaction has its own association constant and dissociation constant. And these constants are numerical values that tell us about this reaction at equilibrium. These constants tell us once this reaction reaches equilibrium, will the vast majority of molecules be in the bounded complex form or in the free non-bounded form. And something else important to realize is both of these constants tell us the exact same information. They're really just the inverse of one another, and they both tell us the exact same information. For example, if you were to flip 5 coins. So let's say we have 3 heads and 2 tails. We could either say that we had 3 heads, or we could say we had 2 tails. They both tell us the exact same information. They're just looking at things from different perspectives. That's the same thing with this association constant, dissociation constant. They tell us the exact same information about this interaction. They're just looking at it from different perspectives. So what exactly do I mean? What are these constants? So let's say we have this cell. We know inside of the cell, we're going to have some free ligand, we're going to have some free protein receptor, and we know eventually some of the ligands are going to bind the protein receptor, forming the complex. But then the ligand's going to pop back off, then it's going to bind again, then it's going to pop off again, and eventually we'll reach these equilibrium concentrations. For example, let's say we've reached equilibrium, and let's say at equilibrium, the concentration of free protein receptor is 4 molar. Let's say the concentration of free ligand is 6 molar. And let's say the concentration of protein-ligand complex, the protein-ligand complex is 2 molar. And we know we're at equilibrium if we reach these concentrations and these concentrations don't change. If these concentrations are not changing, we know we've reached equilibrium concentration. So we can wait 10 minutes, 1 hour, 10 hours. If these concentrations remain constant, we know we've reached the equilibrium concentrations. Now, once we've reached the equilibrium concentrations, we can plug them into this formula to give us the association constant. But what's important to realize is it's the equilibrium concentrations that you plug into this formula. So once and only once this reaction reaches equilibrium and you reach those equilibrium concentrations, it's specifically those equilibrium concentrations that you plug into this formula that give you the association constant. And the way this association constant formula will be set up is you essentially take the equilibrium concentration of the protein-ligand complex and put that in the numerator, and divide it by the equilibrium concentrations of the free protein receptor and free ligand multiplied by each other, and that gives you the association constant. And realize this is a capital K representing an equilibrium constant. So this is just any old equilibrium constant that you learned in general chemistry. So this formula gives you the association constant. Then the reciprocal gives you the dissociation constant, where again, you wait for the reaction to reach equilibrium. But in this example, you take the protein and ligand and put that in the numerator, and you take the complex and put that in the denominator, and that'll give you the dissociation constant. So again, every protein-ligand interaction has its own association constant and dissociation constant. And again, both these values tell you the same information. They tell you about this particular reaction at equilibrium. It tells us what this reaction looks like once it reaches equilibrium. For example, let's say this reaction reaches equilibrium, so we have these equilibrium concentrations, and let's plug them into these formula to get the association constant, dissociation constant. So if we did that, we would get an association constant of 1/12 and a dissociation constant of 12. So now we know this particular reaction with this particular ligand and this particular protein has an association constant of 1/12 and a dissociation constant of 12. But again, both these constants tell us the exact same information. They tell us when this reaction reaches equilibrium, they tell us about the relative amount of protein-ligand complex to free protein and free ligand. And what's important to realize is that the lower the association constant, the higher the dissociation constant, the lower the affinity that this ligand has for this protein. And if you think about it, that makes sense. If they have a very low affinity, then when we reach equilibrium, we'll have very little in the protein-ligand complex form. So again, if this ligand has a very low affinity for the protein receptor, then when this reaction reaches equilibrium, very little of the ligand will be in the protein-ligand complex form. So therefore, we would have a very small amount of protein-ligand complex, and that would be represented in these constants. And that would give us a very low association constant and a very high dissociation constant. So again, the point is, these values tell us about this reaction, and they tell us about the affinity that the ligand has for the protein receptor. But I know this is a little complicating, so let's try another example, and hopefully it'll make more sense. So let's try another example. Let's say we have these free protein antibodies and these free ligand antigens. We know eventually the ligand's going to bind the antibody, then it's going to pop off, then it's going to bind again, and eventually we'll reach an equilibrium. So let's say these are the original concentrations, but again, let's say the ligand binds, then it pops off, then it binds again. And let's say we reach an equilibrium, and let's say these are equilibrium concentrations. So we, at equilibrium, once this reaction reaches the stable equilibrium concentration, let's say we have 1 molar of the protein antibody, let's say we have 3 molar of the ligand antigen, and let's say we have 5 molar of the antibody-ligand complex. So we've reached our equilibrium concentrations. We know once and only once we've reached our equilibrium concentrations, we can plug them into this formula to tell us the association constant that the ligand has for the antibody and the dissociation constant that the ligand has for the antibody. But again, we know both these values tell us the same information. They tell us about this reaction at equilibrium. But just looking at this reaction at equilibrium, what can we conclude? Well, we know once we reach equilibrium, the vast majority of the molecules are in the protein-ligand complex. Nearly all of them are in the protein-ligand complex. So that tells us that this ligand probably has a very high affinity for the antibody. And that's why when we reach equilibrium, so much are in the bounded form. If we had a low affinity, then when we reach equilibrium, barely any would be in the bounded form, but we see most are bounded, so clearly the ligand has a high affinity. So that should be reflected in the association and dissociation constant. And again, it has a high affinity, so we have a lot of the protein-ligand complex form. At equilibrium, we have a lot in the complex form. So therefore, we have a large protein-ligand complex form. So therefore, we would have a high numerator here giving us a high association constant, and a high denominator here giving us a low dissociation constant. But again, these constants tell us about this reaction at equilibrium, which tells us about the affinity that the ligand has for the protein receptor. And again, we explained the higher the association constant, the higher the affinity. So if we were to take both of these reactions, let them reach equilibrium concentrations, then once we reach those equilibrium concentrations, plug them into this formula, we would get these association constants. So we see this guy has a higher association constant, so therefore this ligand has a high affinity for this protein receptor. However, this reaction has a low association constant, so therefore this ligand has a low affinity for this protein receptor. And we can see that. We see when this guy reaches equilibrium, barely any of the ligand are in the bounded form. We have very little of the bounded complex, so clearly this guy has a low affinity. Because if it had a high affinity, then when we reach equilibrium, the vast majority of these molecules would be in the complex form. But again, because we have such a low affinity, that even when we reach equilibrium, very little are in the bounded form. And because we have so little in the bounded form, that would give us a low numerator, which will give us a low association constant, which tells us this guy has a low affinity. However, we have the opposite situation with this reaction. We know when this guy reaches equilibrium, the vast majority are in the complex form. So clearly this guy has a high affinity, and that's why once it reaches equilibrium, so many are in the complex form. So because we have a lot in the complex form, we have a high numerator giving us a high association constant. And again, the higher the association constant, the higher the affinity. So again, hopefully that makes sense. But again, we can plug in these values into this formula, giving us the association constant, but we can also plug them into this formula to give us the dissociation constant. And again, it's essentially the opposite trends. Essentially, the higher the dissociation constant, the lower the affinity. The lower the dissociation constant, the higher the affinity, and it's for all the same reasons. It's the opposite scenario. Because again, we already explained that when this guy reaches equilibrium, the vast majority are in the complex form. So clearly this guy has a high affinity. That's why so many are in the complex form at equilibrium. So we have a lot in the complex form. So therefore, when you plug them into the dissociation constant, we have a lot in the complex form, giving us a high denominator, giving us a low dissociation constant. The lower the dissociation constant, the higher the affinity, which would again be the flip side with this reaction. So again, hopefully by now, you can see these trends. And again, the point is that this is a big picture idea. Every ligand protein receptor interaction has its own association constant and its own dissociation constant. And these constants tell us about this reaction at equilibrium. They tell us when the reaction is at equilibrium, how much are in the bounded form. And that essentially tells us about the affinity that the ligand has for the protein receptor. Because if a lot are in the bounded form, clearly it has a high affinity, and that will be represented in the association constant. So both of these constants tell us the same information, they're just looking at it from different angles. So now I want to switch gears and talk about rate constants. So in general chemistry, you've probably learned about this lowercase k, these rate constants. And you probably learned that every single chemical reaction has its own rate constant. For example, if this ligand binds to this protein, this is a chemical reaction. So this reaction has a rate constant. Every reaction has a rate constant. And the higher the rate constant, the faster this chemical reaction. So you probably learned about rate laws in general chemistry. For example, this particular chemical reaction has its own rate law, which tells you the rate that you form the product, which happens to be the protein-ligand complex. So the rate law for this reaction would be this. So essentially, if you knew the concentration of free protein receptor and multiplied by the concentration of free ligand and multiply that by the rate constant of this particular chemical reaction, that will tell you the rate of complex formation, the rate of product formation. And again, this complex is the product, so that is what this rate law tells you. It tells you the rate in which you form the product, and in this case, the product is the protein-ligand complex. However, we can also have a rate law for this dissociation reaction, because again, once we form the protein-ligand complex, eventually the ligand's going to dissociate, forming these products, this free protein receptor and free ligand. So this reaction also has a rate and also has a rate law. So the rate law for this particular reaction would be this. So if you knew the concentration of protein-ligand complex and multiplied by the rate constant of this dissociation reaction, that will tell us the rate of complex degradation. Essentially the rate in which we form these products, and in this case the product is the free protein receptor and the free ligand. So the point is, every chemical reaction has its own rate law. Where this guy's rate law tells us about the rate of this complex formation, while this guy's rate law tells us about the rate of these product formation. However, the rate of this product formation also is the rate of this complex degradation. The faster we degrade this complex, the faster we'll form these products. So another way of looking at it is this guy's rate law tells us about the rate of this complex degradation. So this guy's rate law tells us about the rate of this complex formation, while this guy's rate law tells us about the rate of this guy's complex degradation. But something really important to realize is, again, we've already explained when we reach equilibrium, the concentrations are not changing. And that's a defining characteristic of equilibrium. So therefore, when we reach equilibrium, the concentration of the protein-ligand complex is stable. When we reach equilibrium concentrations, these concentrations aren't changing, so therefore we have stable concentrations. And the concentration of this protein-ligand complex is stable, it's not changing. So therefore, at equilibrium, the rate of complex formation must equal the rate of complex degradation. These two rates must equal each other because that's the only way to maintain a stable protein-ligand complex concentration. For example, let's say we were quickly forming protein-ligand complex and we were very slowly degrading protein-ligand complex. What would happen under those scenarios? Well, under these scenarios, if we were quickly making protein-ligand complex, but very slowly degrading protein-ligand complex, we would be building more and more and more protein-ligand complex. And therefore, we would not be at equilibrium, because we would see the concentration would be changing, so we would not be at equilibrium. However, if the rate of protein-ligand complex formation equaled the rate of protein-ligand complex degradation, then we would be forming the complex just as quickly as we were degrading it. Therefore, the concentration of the complex would remain stable, and therefore we would be at equilibrium. So another defining characteristic of equilibrium is that the rate of complex formation equals the rate of complex degradation. So therefore, at equilibrium, these two rate laws will equal each other. So we could set them equal each other. So at equilibrium, this will be true. This, representing the rate of complex formation, will equal this, which represents the rate of complex degradation. So again, these two rates will equal each other at equilibrium. This will be true at equilibrium. So now that we have this equation, which we know which will be true at equilibrium, we could algebraically rearrange this equation. And there are two ways we could rearrange this equation. We could divide both sides by this little kd and divide both sides by this p times L. So that's one way. Or we could divide both sides by this little ka and divide both sides by this pl. But the point is, we could algebraically rearrange this equation. So you can play around and algebraic rearrange this equation, and if you did that, we could get these two separate equations. These are both equal that original equation, which we know is true at equilibrium. So therefore, we know both of these equations will be true at equilibrium. And also, remember what we learned earlier. We learned about this association constant equation, and we learned about this dissociation constant equation. But again, we already derived how these equations are true at equilibrium. Now, just doing some simple algebra, we can see that this guy is equal to this guy, which is equal to this guy, which is equal to this guy. So therefore, we can tell that this guy is equal to this guy. And the same thing with this reaction. We know this guy's equal to this guy, which is equal to this guy, which is equal to this guy. So therefore, this guy's equal to this guy. So we could draw that. We know these all equal each other. So therefore, we know these equal each other and these equal each other at equilibrium. Because again, these were all assumptions that are made once we reach equilibrium. But the point is, the ratio of these rate constants equals the association equilibrium constant, while the ratio of these rate constants equals the dissociation equilibrium constant. And keep in mind the difference between these lowercase rate constants and these uppercase equilibrium constants. These lowercase rate constants tell us about the rate of chemical reactions, while these uppercase equilibrium constants tell us about reactions at equilibrium. However, this relationship will be true. So again, that concludes the video on association constants versus dissociation constants. In the next video, we're going to talk about the inhibitory constant, the IC50 and EC50, which are really important complexes you need to know for biochemistry and for the MCAT. So I have a link of those videos below.